In this loop, we will look at in this clip, in this video, we will look at energy associated with current I in a magnetic field. But before we do that, let's go back for a moment to the torque. Torque on loop of current I, so I loop in the magnetic field, in a B field. So what we had was a picture that looked like this. Here you have this loop, and the current I flows along this loop, so it just flows like this. And then we have, let's give it some depth here for clarity. Right, so we have this wedge here. And the magnetic field point, well, actually, first let's state here's the A vector, the vector that represents the area of this loop. It just points out like this, and it's perpendicular to the surface. It's the A vector. And then let's say that we have this whole loop in a magnetic field, and magnetic field points into the plane of this loop in the following way. Well, actually, let's say that the magnetic field actually comes out of the loop and it points in this direction. That'll make my life a little easier. So here's B, it just points like that. So at this location here, I'll draw another B, here I'll draw another B, and then, you know, I could extend this out, and I could say that the magnetic field here points like this, and then here it points like that, and here it points like this, and somewhere over there along that line it points like this, and here it does the same thing, does the same thing. All right, so then the angle between A and B is alpha, and we stated the torque equation as I times A times B times the sine of alpha. Right, A was the current, I was the current, A was the area of the loop, B the magnetic field, and then I just gave you in a picture what alpha was. So it's common to define following: U as I times A, and to be more proper, call this thing a vector because A is a vector. And then we're going to call this the magnetic moment. Magnetic moment. And its units would be, well, amps times meters squared. And then you can rewrite the torque equation as torque equals U times B times the sine of alpha, and that's fine, but you could also write it in a vector form as U cross B. So it's common to write the torque equation on the loop in a magnetic field in this way here. All right, so keep that in mind. Now, now what we'll do is we'll look at the energy, potential energy in a loop, and so maybe we can start doing it here. So I'm going to sort of divide this screen out, and then let's consider the following. So suppose that we have a magnetic field. Let's draw a long magnetic field. Here's one line, here's another line. Nice if they were parallel, but oh well. The first and the third one are parallel. Fourth one is not too bad. The second was a little iffy, but this is your magnetic field, B. And then let's consider, I think, 5 different setups of the loop. So let's say here that you have a loop, same loop as the one above. So we're going to take this loop and we're going to place it now in the magnetic field. So you have the current here that comes out of the page, goes down into the page, goes into the page, and comes back up again, and so it goes like this. See the way the cursor goes, the loop here goes like that. Here's the current I. Right, and then we will take a case where this same loop is now here. Let's rotate it a little. same direction of the current I, and then we have this case here where this loop is now like this. Draw it a little shorter. Current I goes like this, and then we will look at a case where this thing is now here. So that the current I goes up like this, and then we end up with a flipped loop where current goes into the page there, comes out of the page here, and so it flows like that. So this is the direction of the current in this case, I, and here's I. Of course, here's I, and then I guess I'll put I's all over the place. Let's show the vector A for each one. So in this case, now should you draw the vector A to the left or to the right? It doesn't matter, except that in the foresight, I kind of know where I'm going with this, so I will draw it actually to the right. But in principle, it doesn't really matter. So you have 90 degrees here. This is vector A. You have 90 degrees here. This is vector A. You have 90 degrees here, vector A. You have 90 degrees here, vector A. 90, 90, and then the last one would be pointing this way. Here's vector A, 90 degrees as well. And so this vector A kind of shows you how this whole loop rotates around. Now let's draw the forces. So in this first case here, the force on the loop on the top, the force on the section of the loop on the top is going to point, let's see, if the fingers of my right hand point in this direction, the thumb has to come out of the page. Oh, that's going to be tough for me to draw. But anyways, the thumb has to come out of the page, and so let me see if I could give it a better shot. So these fingers here would point kind of like that, and then the thumb comes out of the page, goes like back, like, yeah, well, I give it a shot. But anyways, the force would point down out of the thumb of your hand. Hopefully you can manage by now to do that yourself. So what you would have here is that the force on the segment of the loop here, which would, by the way, be that segment on top, would point down, and so this is force F. On the bottom here, on the other hand, the force would point up, right? And so we would call this setup here this whole loop here is in equilibrium because the forces do cancel out and the forces point in same, equal, and opposite directions, and they would give you no torque. You would have no torque for this setup here. There would be no torque, but this would be an unstable equilibrium because even a little bit of a push in this direction, even if you were to push it, tip it just a little bit in this direction, it's going to offset the two forces. They won't be pointing along the same line, and then this whole thing is going to start to rotate. So this would be an unstable equilibrium. I'm going to label it as such. Unstable equilibrium. Now let's consider, and now at the same time, let's look at, well, okay, let's just keep going. So then the force on this one here would also point down by the same right-hand rule principle. Here the force would point up, and obviously what we see here is that this loop will rotate like that. And here in this case, the force by the right-hand rule again would point down, and here the force by the right-hand rule would point up. And so this thing would continue to rotate. And then here in this case, the force would still point down. Pause. It would still point down, and then here the force in this case would still point up. I'd still have force pointing up, and so this thing would continue to rotate. And then eventually when I get to this spot here, what I would have is that this force on the top would so this force here would point like this, and then here the force on the bottom would point like that. And these forces here are aligned again. They point along the same axis, same line of action, and so there would be no torque. I have torque here, I have torque here, I have torque here. Here my torque is 0. Here my torque is 0. So I found another equilibrium, except that this would be a stable equilibrium. Stable equilibrium. meaning that even if I push this thing a little in this direction, it's just this whole loop here is going to simply come back to where it was. It's going to go back to its equilibrium position, right? Versus if I go to this one here, if I push this a little off, I'm going to get this whole rotation going until I end up in this spot. So on the left, I have an unstable equilibrium. On the right, I have a stable equilibrium. That's the first thing you should notice. The next thing is that well, let's consider what's happening here in terms of kinetic energy. So let's state this maybe in blue. All right, let's do it in blue. So here I have kinetic energy being 0, and here I also have kinetic energy being 0. Here's where I have kinetic energy being at its maximum. So this here's kinetic energy is the maximum. This point here, kinetic energy is increasing. And then when I finally get to this point here, and kinetic energy is decreasing so that it eventually can become 0, right? So here kinetic energy is getting smaller until eventually it becomes 0. Now the potential energy, this would be the lowest potential energy I could have. So I'm going to write this as this is a minimum I could have. There's no energy stored in this system that I could use to turn this, to give it some kinetic energy. Right in here, versus in here, there's got to be a lot of potential energy because there's quite a bit of potential to get rotation going. And so I'm going to end up with, this is a place where my potential energy is at its maximum. So here's the maximum potential energy. And you get something unusual perhaps, but not really, something maybe counterintuitive at first, but you end up with maximum potential energy here, and you then minimum potential energy here. That I think should make sense, because you have quite a bit of energy stored in this system, since all of this rotation can follow out of it. In this case, there's really no potential energy. There's no energy stored in this system, because you can't draw any kinetic energy out of this setup. Now this is where you're going to get maximum kinetic energy right at the center. This is where at this point the loop is going to rotate at a highest omega, highest angular speed. Put here highest omega at this point. So so keep this in mind, and now let's try to determine the actual expression for potential energy of a loop in a field. So maybe what I'll do is well, let's just go down. Let's just go here. All right, so in general, potential energy, expression for potential energy is F dot dr, right? Or which is that potential energy is work done by a force, and in this case would be force times what would be the line integral of force and displacement. But for our specific case, this can be turned into, and it can be shown, but I'm just going to give you the result that this could be torque. It could be written as torque d theta. Now we have the equation for the torque. So, and specifically, this would be torque, the magnitude of the torque. And so that would be mu cross d theta. And that becomes mu d sine alpha theta, and what I have to, and of course mu is a constant. This is remember that mu is I times a, so a of the loop doesn't change, current stays the same, so this is a constant. Magnetic field is a constant, so this can be pulled out, and so what I have is mu b sine alpha d theta. Now theta is the angle between, so let's put this here, theta, that's the angle, well, theta is the angle of the whole rotation. Theta is the angle through which the object rotates. And the angle through which the object rotates is, well, let's see how that goes. So how about we come back to this one in a second, and let's figure out alpha. Let's look at alpha first, and that should help. So alpha is the angle between A and B. Now alpha in this case is going to be 180. This is 180 degrees. Alpha in this case is, it's hard to tell exactly what it is, but it's probably A points this way and B points in this direction here. And I'm looking at 90 plus maybe 45. So let's say here alpha is 135 degrees. Here alpha is just 90 degrees. 90 degrees. B points to the left. Right? B points to the left and then A points up. So it's 90 degrees. Here alpha in this case would be simply about 45 degrees. And in this case here alpha would be 0 degrees, right? Both A and B both point in the same direction. So alpha goes from 180 to 0. Or if I flip the direction of A, it would go from 0 to 180. And then theta is the angle through which this thing rotates. I'm going to write here angle of rotation of the loop. In other words, theta is alpha. If alpha goes from 0 to 180, or if you wish to go this way from 180 to 0, and theta would be the same thing because theta rotates through 180 degrees. And so what I can do is I can have to, well, these two correspond to each other. So really what I should write is that the potential energy is U, oh, I lost the negative sign. We should bring that negative. UB times the integral of sine theta d theta. And I'm just integrating this from some angle to, from 0 to some angle theta, the angle of the actual rotation that I want to integrate this through. But I do need the negative here. So there's a negative, that negative comes out. So I have negative, and then this becomes negative here as well. And so now what I get out of this is, wait, pause. No, we don't need the negative. The negative doesn't belong there. Negative is about to come up. Just remember that there's a negative in this whole thing, but it's not there yet. It's to come. In fact, this is where it comes. So what I get out of this is minus UB cosine theta from 0 to angle theta, and I'm just going to plug these values in, and so what I end up with is minus UB cosine theta minus plus UB. Or better yet, what I could do is, it'll be easier to get rid of this. It'll be easier to do the following. If I get rid of that, and I get rid of this, and instead of making it a definite integral, what I'm going to do is I'm going to make this an indefinite integral. It'll be easier to explain something for me. So minus UB cosine theta is what I get out of the integration plus a constant, right? Plus some constant C. So what I have is an expression for potential energy that looks like this. Minus UB cosine theta plus a constant C. Right, now, constant C, that's, what do we do with it? Well, we're going to get rid of it. It's going to cross this thing out. Now here's why we can do that. Remember, potential energy is, you can determine what you measure the potential energy relative to. So if this is the table, and here's the floor, and here's the ceiling of a room instead of a house, then suppose you have an object of mass m at this location, how much potential energy does it have? Well, that's a meaningless question unless you ask relative to what point. So it will have some amount of potential energy relative to the floor. That would depend on h1. It would have a different amount of potential energy, in fact less, relative to the surface of the table. That would depend on the height h2. And it would have a different amount of potential energy relative to the peak of the house. In fact, that would have, at this point, relative to the peak of the house, it would have negative potential energy. So, and that would depend on h3. Right? Potential energy, gravitational potential energy is mgh, and so everything depends on h, on height h. You can choose the reference point to which you measure your potential energy. And so that's always true. And so the same thing with this one here. You can choose the reference point to which you measure your potential energy. In other words, forget the constant and just choose just use that. And this is what we'll do. The equation for potential energy is in fact minus u b cosine theta, which by the way turns into minus u dot b. Okay, so now we have an expression for the potential energy, though we still have to grasp it because there's something interesting there that shows up in that. All right, so I redrew the picture, and then let's see if we can try to understand this equation, or rather, the equation is not difficult to understand, but let's see if we can understand how to properly use it. So we have kinetic energy being 0 at this point, kinetic energy being maximum at this point, kinetic energy being 0 at this point. This is, I should add this. This here is a stable equilibrium, and this here is an unstable equilibrium. All right, now this is where we have the maximum potential energy. So I'm going to put here, this is potential energy is at its maximum, and then here the potential energy is at its minimum. Note that I never said in this whole presentation that this potential energy is 0. I simply said that this is minimum, and you're about to see why that's the case. So now let's state, let's also add to this picture the angle theta. So angle theta is the angle, this angle theta here in this equation. This angle theta is the angle through which the object rotates. All right, so the angle here hasn't, the loop here hasn't rotated through anything yet, right? Here it's just, it's rotated through the angle of 0. But actually this is not helpful. Don't think of this as the angle through which the object here rotates, but rather think of this as the angle between A and B, or the angle between U and B. So theta is the angle between U and B, and that amounts to saying that theta is the angle between A and B, because remember that U is defined as I times A. So let's state what this angle theta is. Well, theta here is 180. That's the angle between A and B. The theta here is something, let's see, so between A and B, that would be like something like 135, assuming that you have 45 degrees here, but here theta would be 90. Here theta would be maybe close to 45 degrees, and then here theta would be 0 degrees. All right, and then let's see what that does to the equation. So potential energy, the actual expression for potential energy then becomes UB, right? Because cosine of 180 is -1. Potential energy at this point would be 0, because cosine of 90 is 0. And then potential energy at this point becomes minus UB, because cosine of 0 is 1. And so you have that this is the maximum potential energy. This is just potential energy in the middle. And then this is the minimum potential energy. All right, so it's you know, your minimum potential energy is not 0. Just keep this in mind. All right, so the next thing is to solve a few problems. You'll see that the problems are easy as long as you keep this in mind. Oh, one more comment is that sort of interesting. What happens here is that the equation for potential energy is minus U dot B, and the equation for the torque is U cross B. One is a dot product, the other one is a cross product. Okay, so then the next thing is to solve a sample problem.